Welcome to Tales from the Periodic Table. I'm your host, Ron Hipschman, and today we're going to talk about the element dysprosium. I have a little sample of it right here. I don't know if you can see that. It's a little bit hard to see. So let's go back to our presentation because I put it on my scanner so that you could see it a little bit closer up. It's a shiny silvery metal when kept inside the glass vial away from oxygen. Here we see the beautiful periodic table produced by Theodore Gray. As I've mentioned in previous episodes, Theo has written one of my favorite books called The Elements, which I encourage you to pick up. Check out his fantastic website, periodictable.com. Dysprosium is the 66th element in the periodic table. Its atomic number is 66 because that's how many protons are in its nucleus, and that is what distinguishes it as a unique element. In 1878, erbium ores were found to contain the oxides of holmium and thulium, elements we'll get to in a bit. French chemist Paul-Émile Lecoq, while working with impure holmium oxide, separated dysprosium oxide from it in Paris in 1886. Lecoq was only able to isolate dysprosium oxide after more than 30 attempts at his procedure. The difficulty of extraction led to the naming of the element. From the Greek dysprositos, meaning hard to get, he named the element dysprosium. The element was not isolated in relatively pure metallic form until after the development of ion exchange techniques by Frank Spedding at Iowa State University in the early 1950s. I really like the university's motto, "Science with Practice." One commercial source of rare earth elements is the mineral monazite. Monazite is a phosphate with lanthanum, cerium, praseodymium, and neodymium as major substituting elements, and most of the other rare earths as minor constituents. It's usually found in the form of a sand with other minerals. India, Madagascar, and South Africa have large deposits of monazite sands. Another source of rare earths, including dysprosium, is the mineral bastnasite, which is a carbonate fluoride, with lanthanum, cerium, praseodymium, or yttrium as major substituting elements. Both monazite and bastnasite are mined for many rare earth elements. I have a couple more rare earth-containing minerals for you. First is fergusonite, which is a yttrium niobate mineral which might contain other rare earth oxides, here shown as REE for rare earth elements. This was named after the colorful Robert Monroe Ferguson of Raith, who was an amateur in mineralogy. Another rare earth-containing mineral has the coolest name, xenotime. This is normally a yttrium orthophosphate, but other elements can take the place of yttrium, including the element dysprosium. Let's take a look at the rare earth content of 3 of the previous minerals. You can see from this table, dysprosium appears in low percentages in these minerals, accounting for only 0.03% of bastnasite, up to 1.15% of monazite, and up to 8.7% of xenotime. The only rare earth mining and processing facility in the United States is the Mountain Pass Mine, 53 miles southwest of Las Vegas. The mine supplies almost 15% of the world's rare earth production. While this mine specializes in praseodymium and neodymium, they also extract other rare earths, including dysprosium, as byproducts. Dysprosium belongs to a row of elements known as rare earth metals or lanthanides, since lanthanum is the first element in this periodic table row. Dysprosium is the 10th element of this series. Technically, Both scandium and yttrium are also included in this group since they're both members of the same periodic table column. Both the lanthanide row and the actinide row below it actually fit in the two spaces after barium and radium. But if we displayed the table in this fashion, it becomes too long and unwieldy to fit in books or on posters. As with most elements, the price of dysprosium varies widely with purity and the quantity you buy. 99.5% pure dysprosium goes for about $430 per kilogram in large quantities, a little more than the other rare earth elements we've encountered. The element dysprosium is uncommon in the universe, coming in as the 55th most abundant element in the universe by mass, about 2 parts per billion. At 52nd, dysprosium is about as abundant in the Sun, also at 2 parts per billion. It's the 50th most abundant element in meteorites, about 270 parts per billion. In the crust of the Earth, it's the 39th most common element, almost 6.2 parts per million, slightly more common than iodine and tin. Dysprosium is the 63rd most abundant element in the oceans, virtually non-existent at 91 parts per trillion. And lastly, and not surprisingly, there is no dysprosium in us. This complicated version of the periodic table shows the evolution of the elements through the history of the universe. Here, you see each element square with a tiny chart of its own showing that element's growth over the age of the universe by various processes. Dysprosium is here. I understand this looks complicated, but let's look at just dysprosium a little closer. The horizontal axis of this square represents time from the Big Bang to now. The vertical axis shows the proportion of dysprosium created by various processes. The majority of dysprosium present today is believed to be produced in supernovae, the yellow area. About 1/6 is produced in dying low-mass stars, the magenta area, and a small amount, that green sliver on the top, is produced in neutron star mergers. Note, the dysprosium produced by dying low-mass stars, the magenta area, doesn't get started until a bit later in the history of the universe. That's because low-mass stars exhaust their nuclear fuel much more slowly, and they last a long time before they start dying. Each element has many different forms. For each specific element, the number of protons in the nucleus is the same, 66 protons for dysprosium, but there can be different numbers of neutrons in the nucleus. All these different forms are called isotopes. They're chemically identical to each other, but with slightly different weights. The number you see next to the chemical symbol is the total number of protons and neutrons in the nucleus. There are 36 known isotopes of dysprosium, and of these 36, there are 7 stable non-radioactive isotopes. These isotopes occur in nature in varying amounts, as you see here. By the way, the word isotope comes from the Greek isos, meaning same or equal, and topos, meaning place, since all these various forms of dysprosium occupy the same place in the periodic table. Of the radioactive isotopes of dysprosium, these are the longest lived, the ones with half-lives over 1 hour. More about half-lives in the next slide. The longest-lived isotope is dysprosium-154, with a half-life of 3 million years. What's a half-life? This graph shows an exponential decreasing curve. As an example, let's say we start with 1,024 atoms of any of the isotopes from the previous slide. You'll see why I chose 1,024 atoms. Hint, it's a power of 2, and we're going to be doing a lot of dividing by 2. If you wait 1 half-life, half of your isotope will decay, and you'll have 512 atoms left. If you wait 1 more half-life, half of that half decays, leaving you with 1/4 of the original 1024, or 256 atoms. Another half-life, half again as many, or 128 atoms, and so on. Just keep dividing by 2 every half-life. After 10 half-lives, you'll have about 1/1000th of your original amount. By the way, notice there's 1 remaining atom after 10 half-lives in my example. If you waited 1 more half-life, your remaining atom would have a 50-50 chance of decaying in that time. Dysprosium has a medium density at 8.551 grams per cubic centimeter. As a reminder, water has a density of 1 gram per cubic centimeter. I've put up some more densities for you here. You can see that dysprosium is a bit denser than iron at 7.89 grams per cubic centimeter. Here's a graph of the elements from highest density to lowest density. When I do this talk with an actual audience, I have a set of blocks so you can feel density for yourself, but we'll have to wait to do this until we're back face to face. My set of blocks have a wide range of densities, with the densest at tungsten, to lead, to copper, to iron, to titanium, to aluminum, to magnesium. I also have plastic and wood blocks, but those are not technically elements. Again, dysprosium's density is 8.551 grams per cubic centimeter, the magenta circle just above iron. Dysprosium has a fairly low melting point at 1,412 degrees Celsius, or 2,563 degrees Fahrenheit. It boils at 2,567 degrees Celsius, that's 4,653 degrees Fahrenheit, 1,155 degrees Celsius above its melting point. A fair difference. If we compare the size of dysprosium to that of hydrogen, we'd see something like this. The dysprosium atom is 4.3 times the size of hydrogen. Those outer 2 electrons are held fairly loosely, making for a larger atom. By the way, a picometer is a trillionth of a meter. Atoms are very small. Here are atom sizes from largest, cesium on the left, to smallest, helium on the right. Dysprosium has the 9th largest size atom of all the elements. All the rare earths are fairly large. I'll mark the other lanthanides in blue. Notice how they're all clustered towards the top of the chart. They all have those loosely held outer 2 electrons. Dysprosium is a moderately soft element, coming in at 1.8 on Mohs scale of hardness. You could scratch it with your fingernail, which has a hardness of 2.5. Dysprosium does not expand much when you heat it. It has the 46th highest rate of thermal expansion, about 10 parts per million per degree Celsius. This means that if you had a 1 meter long bar of dysprosium, we're going to have to magnify this by a factor of 10 just to see it, and you heated the bar by 1 degree Celsius, it would get longer by only 10 millionths of a meter, about 1/5 of a hair width. Dysprosium expands only 3.8 times as much as the least expansive element, silicon. Here's the periodic table of the spectra. Dysprosium has a complicated and weak set of emission lines. Not a lot to see here, but still a unique identifier of the element. Let's take a look at a few applications of this rare earth element. Some are a bit esoteric, but I'll do my best. This is not technically an application, but many elements are incorporated in this form of lamp called a hollow cathode lamp to give scientists access to the spectrum of pure elements. In metal-halide arc lamps, the inclusion of dysprosium iodide in the arc bulb changes the light emission of the lamp. If we looked at the spectrum, The dysprosium enhances the blues and yellow-greens, making the light whiter when seen in combination with other elements in the lamp. Before we get to the second application, I want to talk about something called the Curie point. If an object is attracted to a magnet, like this nail, and you heat that object up, it will eventually reach a temperature where its molecules will be moving so chaotically that they will no longer be able to maintain alignment with the local magnetic field. This destroys the object's ability to be magnetized and attracted to a magnet. This is a little over 1,000 degrees Celsius for iron. A standard neodymium magnet, actually made from neodymium, iron, and boron, reaches its Curie point at about 350 degrees Celsius. Adding rare earth elements, such as terbium and dysprosium, can increase the Curie point and hence the magnet's working temperature by a significant 50 degrees Celsius. The drawback of this method is that dysprosium is a moderately expensive additive. It is, however, useful in places such as electric car motors, like my Volt, and power-generating wind turbines. The magnetic properties of dysprosium can make it useful in the platters of hard disk drives inside your computer. If you take the cover off your hard drive, don't do this unless you want to destroy your hard drive and all the data in it, you would see the magnetically coated platter where information is stored. Also, beneath the silvery cover in the upper left, you'd find a rare earth magnet used to move the read-write head across the spinning disk. Rare earths are important in many ways to data storage. Chemist Selvin Demir and her team at Michigan State University created a molecular magnet with dysprosium. The ball and stick model you see here is that molecule. The two magenta balls are terbium or dysprosium atoms. The green balls are bismuth atoms. The gray caps above and below the magnetic cube are rings of carbon atoms with hydrogen atoms attached. This configuration forms a one-molecule magnet that one day may allow higher capacity data storage and quantum computing. Right now, the molecule is only magnetic near absolute zero. Terfenol-D is a unique alloy made of terbium, the ter and the previous element in this series, iron, Fe is the chemical symbol for iron, and dysprosium, the D in Terfenol-D. It's about 40% iron with the remaining 60% terbium and dysprosium combined. Why is this alloy unique? I spoke to Dan Bino, CEO of TD Vibe LLC, the only manufacturer of Terfenol-D. When placed in a magnetic field, Terfenol-D changes shape, and by a lot, 1 part in 1,000. Let's take a look. Some objects will change their shape when put in a magnetic field. This is called the Magnetostrictive effect. If we take a bar of Terfenol-D and put it inside a coil of wire, this is called a solenoid, when we hook up the coil to a power source, a current flows in the wire, creating a magnetic field inside the coil. The Terfenol-D bar responds by changing shape. The bar can get longer, or shorter if we reverse the current. Applying an AC current will cause the bar to oscillate in length. If attached to some mechanism, the bar can apply a tremendous force. Soundbug was a speaker device containing a solenoid or coil of wire like we just saw, with a small bar of Terfenol-D. When stuck to a window or a wall and fed an electric signal, the vibrations of the Terfenol-D make the window or wall into an unexpected speaker. As far as I can tell, this device is no longer available, but a British company, Phionic, makes a similar device for commercial applications also using Terfenol-D. Terfenol-D can also be used to make sound waves in water. The powerful pings of sonar are made with Terfenol-D transducers. If there happens to be a submarine beneath our ship, the sound will bounce from the submarine's hull, reflecting back to the ship, revealing the presence of the submarine. Arrays of sonar transducers in a multi-beam sonar can be used to build pictures of the ocean's floor, mapping the topography of the bottom. Some of these are accurate enough to image sunken ships, like you see here. Adding a Terfenol-D actuator to a lathe tool holder can allow a machinist to cut with micron or millionth of a meter accuracy. This one's a bit complicated to explain, but dysprosium has a high probability of capturing slow neutrons like the ones we find in a nuclear reactor. This prevents the neutrons from participating in the fission process. Most of the rare earths fall near the top of this chart, and a few lanthanides are better at absorbing neutrons than others, but dysprosium is pretty good. If you're building a nuclear reactor, you want tight control of your fission process that's going on inside the reactor core. Fission of the uranium atom happens when it's hit by a stray neutron. The extra neutron destabilizes the nucleus, which then splits into two smaller, lighter nuclei. It also releases a few additional neutrons. The additional neutrons are now free to cause more uranium to fission. Since many neutrons are released by a single fission, and each neutron can cause a further uranium atom to fission, the reaction can grow exponentially quickly. You might want an uncontrolled exponential release of energy if you were developing a nuclear weapon. To control the fission reaction, you need to absorb a critical number of neutrons. Some elements, like cadmium and dysprosium, are very good neutron absorbers. In a nuclear reactor core, control rods of these absorbing elements or their oxides are interspersed among the uranium fuel rods. Pulling the rods out of the core allows more neutron reactions to take place, heating up the core. Pushing the rods in slows the reaction, cooling the reactor. Your body does not use dysprosium, but it probably contains a few micrograms absorbed from the environment. As usual, we'll end this talk with Mary Soon Lee's elemental haiku about dysprosium. In Terfenol-D, pulse to the magnetic beat, expand, contract, dance. In the next program in this series, we'll examine the next lanthanide element, holmium. I hope you'll join me. I'm your host, Ron Hipschman. Thank you for watching this Tales from the Periodic Table program about dysprosium.